Welcome to Lecture 7. Before we start, we are going to refer you to example 1.6 from Chapter 1 from our Rick Duret's Elementary Probability of Application. Alright, so the question there states that if there are 30 students in a class, what is the probability that no two of them have same birthday? So this is a simple worked out problem depending on the idea of independent events happening together. So I hope you can understand it on your own. So now, as you know that if two events are independent or multiple events are independent, the probability of the compound events to happen equals to the product of the individual probabilities. Now, there might be events where you cannot identify them as independent or not at the very beginning. Okay, so how to check independence? First, if there are two events A and B, say A is an event and B is an event, and you don't know whether these two events are independent, so you have to determine P of A first, and then you are going to determine P of B, and then without the help of our formula, you have to manually calculate the probability of A intersection B, all right? And then you are going to check if P of A times P of B equals to P of A intersection B is true or not, okay? So if this holds, then you can say that yeah, A and B are two independent events, and if it doesn't hold, that means both of the events are dependent. All right, so we are going to learn about dependent events at large in our conditional probability lectures. This is not only true for two events. Suppose there are four events and you want to find out whether these events are pairwise independent or not. So the first thing you have to do is determine these four probabilities, all right? And then you have to find out what is the value of P of A intersection B intersection C intersection D without the help of the formula. Then we are going to try to satisfy the formula that P of A intersection B intersection C intersection D is P of A times P of B times P of C times P of D. Okay. So if this equation is true for our events A, B, C, and D, we can say that yes, A, B, C, D are pairwise independent events. So let's see an example. Draw a card from the deck randomly. Event A is the event of the card being a king, and event B is the card is a heart. Okay, so yeah, these are two events. So if you cannot readily state whether these events are independent or not, you are going to check it using the formula stated above. You want to know if A and B are independent or not. I'm sorry for the noise. Yeah, that's what you are concerned about. First, you have to determine P of A. P of A is the probability of getting a king from the deck of cards. So you know that there are only four kings from four of the suits. So the number of favorable cases here is 4, and the total number of outcomes is 52. That means you can pick a card randomly from the deck of cards in 52 different ways, and 4 of these ways are your expected. So it becomes 1 by 13. All right. Now probability of B. What is the probability of the card to be a heart? Okay. So you know that there are 13 hearts there. So 13 is the number of favorable cases, and similarly 52 is the number of total outcomes. Therefore P of B will be 1 by 4. Now, instead of using the formula for independent events, which is P of A intersection B equals to P of A times P of B, we are going to determine P of A intersection B manually, all right? Because we would use the formula if we knew that A and B are independent. Since we don't know about A and B's relation, therefore, we cannot use the formula here. So P of A intersection B. What does A intersection B mean? A intersection B means the card drawn is both a heart and a king. So that means it's the king of hearts. All right. So you know that there's only one king of heart in the deck of cards, right? So the number of favorable cases here is 1, and the total number of ways to pick a card is again 52. Now we're going to check if the formula of independence is satisfied by our probabilities. All right, here. So now P of A times P of B will be equals to 1 by 13 times 1 by 4, which is 1 by 52. And P of A intersection B is also 1 by 52. Therefore, we can say that yes, our formula of independence is satisfied by both of these events. So we conclude that A and B are independent. All right. So before we would knew the events are independent and we would use the formula. Now, as we don't know whether A and B are independent or not, we are going to satisfy the equation first and then state about the independence. So this is example 1. Let's see another example. Draw 2 cards. Now event A is the first card is a dice. Event B is the second card is a die. So we are going to determine if both of these events are independent of each other or not. Okay, so comment on the independence. Okay, yes. Solution. So now we are going to determine P of A again. So what is the probability for the first card to be a diamond? So we know that there are 13 diamond cards there. So 13 by 52, just like the last example here. So similarly, for the second card to be a die, the probability would be 13 by 52. Okay. Now we have to determine the value of P of A intersection B. So what is A intersection B? A intersection B means the first card to be a diamond and the second card to be a diamond together. All right. So to determine this value, we are going to use a bit of counting here. We have to calculate in how many ways the first card can be a diamond. So there are 13 cards available, and then once it's chosen, there are 12 left in the deck. And if we want the second one to be a diamond as well, then there are 12 cards available. So 13 times 12 is the number of ways both of the cards can be diamond. All right. For the denominator, we have to determine the number of ways we can choose 2 cards one after one. So there are 52 different options for the first card to be chosen. And once the first card is drawn, then for the second card we have 51 options. So 52 times 51 is the number of ways to pick 2 different cards. All right. So this is the probability, which reduces to it's 4, it's 3, and then it's 17. So 1 by 17. All right. So P of A intersection B, which means both of the cards to be a diamond, has a probability of 1 by 17. Now we are going to compare the value of P of A intersection B with the value of the product of P of A times P of B. Okay. So this is 1 by 4 times 1 by 4, which is 1 by 16. And clearly, P of A intersection B is not equals to P of A times P of B. Therefore, we conclude that A and B are not independent events. Let's see example 3. It states that suppose you are rolling 2 dice. Event A is the sum of the results is 9. Okay. And event B is the second die shows 2. So are these 2 events independent? You have to comment on that. Okay. So yes, let's start solving this problem. We'll start with evaluating P of A, which means what is the probability that the sum of the results is 9? So for the sum to be 9, if we start with 1 from the first die, the second result has to be 8, which is not possible. So 2, 7 is not also possible. Therefore, we'll start with 3, 6. So this is acceptable. Similarly, 4, 5. 5 4 and 6 3. So these are the only 4 possible pair of outcomes in event A. Therefore event A's cardinality would be 4. So 4 is the numerator. Now what is the denominator? The denominator will be how many different outcomes are possible from 2 dice rolled together. Okay, so we already know that there are 6 times 6 36 results in total, so the answer would be 1 by 9. Okay, similarly for P of B, the second die shows 2, so we want 2, only one outcome is acceptable, and total 6 outcomes are possible from die 2, therefore 1 by 6. Now P of A intersection B has to be calculated manually without the help of our formula of independence. Okay, and then we are going to compare P of A intersection B with the product of P of A and P of B. So P of A intersection B means what? The probability that the sum is 9 and the second die shows 2. Both of these events have to happen together. Now, if the second die shows 2 and the sum is 9, then the first result has to be 7. But it's not possible because a die has only 6 faces with 1 to 6 written on each of the faces. Therefore, A intersection B is a null set. Therefore, A intersection B's cardinality would be 0. So 0 by the number of total outcomes would be also 0. Therefore, P of A intersection B would be 0. Right? So we can see that A intersection B equals to 5 means they are disjoint events. A and B are both disjoint events. Both of them cannot happen together, or both of the events do not share any outcome. So this is something we're going to recall while we're done solving this problem. So P of A intersection B equals to 0. Now it's time to compare. So 0 is not equals to P of A times P of B because it's equals to 1 by 9 times 1 by 6, which is 1 by 54. So 0 is not equals to 1 by 54. So we can conclude that A and B are not independent. Okay, we are done with this problem, and here's something to see. That is, if two events A and B are disjoint and the probabilities are non-zero, right? That means the probabilities are greater than 0. P of A is greater than 0, P of B is greater than 0, and the events are disjoint, which means P of A intersection B equals to 0. So we know that the product of P of A and P of B will never be equals to 0. Since both of the figures are greater than 0, so we'll have a positive product here, but P of A intersection B is equals to 0. So we can come to a conclusion that if two events A and B are disjoint, which means A intersection B equals to null, and P of A greater than 0, P of B greater than 0, then A and B are not independent, because this P of A intersection B will always be 0, and the right hand side will be some positive figure, which is the product of P of A and P of B. So A and B cannot be independent events if both of the events are disjoint and both of the probabilities of those events are greater than 0. Now, if you want to see similar examples, you can check example 1.9 and 1.10 from our chapter 1 of Richter's elementary probability book.